Hello, everyone. I will begin. And welcome back. We will continue our sessions. And now let me introduce our next session chair. Okay, let's welcome next one.
Hello, good morning. Good morning, everyone. Good day. I cannot share my screen.
Sorry.
That's okay. So I'm very happy to join you here at MICAD 2020. First, a small word about me. I am Nashwa Baker. I'm postdoctoral researcher at INRIA Grenoble Alpes from France. And my research interests are computer vision and deep learning. Here's my webpage. Don't hesitate to contact me. So in this oral session, we're going to talk about medical image segmentation, registration, and reconstruction. We will have 1 hour of oral session, and we will have 5 interesting papers. Just a gentle reminder, each paper will have 10 minutes and probably 2 to 3 minutes for questions. So without further ado, let's invite the first speaker, Priynka Sharma from University of South Pacific in Fiji. Please start your presentation.
Hi there, I'm trying to share my desktop. Just give me a second.
Yeah, take your time.
Thank you. Good morning, everyone. I am Priynka, and today I'll be presenting to you on the art of hyperparameter optimization with desirable feature selection. With me in this research, I have Dr. Kailash Chaudhary and Associate Professor MGM Khan. We are from School of Information Technology from University of the South Pacific, all the way from Suva, Fiji. So our outline for this presentation is organized as we will begin with introduction, followed by our aim, objective, a little bit of background with problem statement, our data set information, experiment setup, results, and finally conclusion. Moving towards our introduction. Our introduction is more grounded on towards machine learning algorithms. So in fact, machine learning algorithms are used everywhere from a smartphone to a spacecraft in current modern era. So these algorithms automatically adjust or rather learn their internal parameters based on data. However, there is a subset of parameters that is not learned in fact and have to be configured by an expert. Now, such parameters sometimes or are referred to as our hyperparameters, and they have a big impact on our life as we use AI in our daily activities. The performance of our model can drastically depend on the choices of our hyperparameters. So since the goal of an algorithm is grounded heavily or rather dependent on the data types and the data volumes that rather change from one project to another, there is no single best choice for hyperparameter volumes or other values that fits all models and all problems. Instead, hyperparameters must be optimized within the context of each machine learning project. And therefore, our figure 1 shows the portrayal of the HP schemes that we have utilized. Our aim was, in fact, to control an automated approach in utilizing optimization possibilities, meaning we deliberate more about the issue simultaneously, choosing a learning algorithm and its hyperparameter going past work that usually tends to address this issue in isolation. We have showed that the issue by completely automated approach utilizing ongoing developments in machine learning. So our research objective was to actually locate the current model coherence between the prediction identified and the estimated errors. We had a problem statement which highlights that in many cases, there is huge assortment that is needed in applying machine learning, and this is particularly important in context of our auto ML. So in order to improve the performances of machine learning is not simple by just tailoring them to a problem by hand at initial stages, but rather with the proofs that different methods can be compared fairly if all they receive the same level of tuning problem by hand. So currently every machine learning system has its hyperparameters, and most basic task in automated machine learning, known to be as auto ML, is automatically set these hyperparameters to optimize its performances. The same kind of machine model eventually can require different constraints, for example, weights or learning rates to generalize different data patterns. Now, these measures are called hyperparameters and have to be tuned so that the model can optimally solve the machine learning problem. The hyperparameter optimization finds a tuple of hyperparameter that yields an optimal model which minimizes our predefined loss functions on given independent data. So the objective function takes a tuple of hyperparameters and it retains the associated loss. And henceforth, we have used cross-validation to estimate this generalization or general performances at this point in time. Our dataset information is as portrayed in table 1. The experiment, this experiment dataset was actually downloaded from Virus Shareware, a website that keeps up a continuously updated database of the malware. So to analyze these samples, the initial researchers, they used Cocoon Sandbox just to automate this analysis. And henceforth, we acknowledge Dr. Daniel for his data sharing. Moving on to our methodology, or rather the experimental setup. So figure 2 shows the optimization strategy that in fact we utilized. So we can say that a typical optimization procedure just defines the possible set of hyperparameters and the metrics to be maximized or rather minimized for a given problem. Therefore, our method of, or rather for optimization procedure follows these classical steps as depicted in the diagram, which is figure 2. And we have utilized the Weka tool. So to achieve the objective of this research, the classification method on ransomware detection dataset were applied through Weka environment. And Weka, what is Weka? Weka is the best state-of-art facility for making machine learning systems and the applications to genuine information mining, such as anomalies. It comprises ML algorithms for information mining assignments, and Weka executes algorithm for information pre-processing, such as classification, regression, clustering, association rules, so on and so forth. So moving to our results, that was the test control as portrayed in table 2. We used the tuning test control, and we have, so we determine the most relevant features through the knowledge based on the data observation. And we have used the feature evaluator as gain ranking filter, and evaluation mode was evaluating on all training data set. And we managed to get out from our result the most relevant features of each class, which is depicted in figure 3 that shows the most relevant features out from all for each class. So table 3 was the final optimum result that we obtained, whereby in each we have tested 10 algorithms in total with HPO and without HPO. So there were actually 14,631 extracted features with 1,522 instances that were initially loaded. However, a total of each ML algorithm or rather 6 algorithm configuration were evaluated 50 times with 5-fold cross-validation multiplied by 10 repeats. And then we compared the algorithm configuration based on the percentage of accuracy. Thus, the results that we achieved were impressive, right? And 10 ML algorithms in total were used for this research. Furthermore, feature ranking and file transformation in ARFF were further performed with, again, Weka tool. So in each model analysis, we set the K value, which was 10, and it encapsulates the number of base classifiers. And henceforth, we took n is equal to 5 for cross-validation and weight assignments independently. So to achieve the best outcome, feature selection method along with tuning methodology, as shown previously, made an impact on the performance level of the land model as portrayed in table 3. So finally, the conclusion. The results just shown in table 3 demonstrate that AutoWeka is ineffective at optimizing its given objective function. However, this is not sufficient to just allow us to conclude that it fits model that generalize well. So as the number of hyperparameter of a machine learning algorithm grows, so does its potential for overfitting. The use of cross-validation substantially increases AutoWeka's robustness against overfitting, but since its hyperparameter space is much larger than the standard classification algorithm, it has an important to carefully study whether or not to an extent of overfitting poses a problem. So finally, to conclude, AutoWeka makes it simple for non-specialists, for example, our novice researchers, especially to assemble great classifiers for any application situations just to reduce time and resources. So thank you so much. That was a short presentation by me. And if you have any question, clarifications, please feel free to email me on priynka.sharma@esp.ac.fj or either contact me. So thank you so much for today. Thank you.
Thank you, Priynka, for the presentation. Indeed, the hyperparameter optimization is an important aspect of machine learning design, and it's almost important in every domain uses machine learning. So let's see if we have questions from the audience. Please, if you have questions, post them in the chat or in the Q&A section. I have a small question waiting for others about the AutoWeka. So is the AutoWeka available? Is it an open source tool? Priynka?
Thank you, ma'am, for your question. Yes, it is an open source tool which was initially initiated by a university in New Zealand, Waikato University. So it's very easy and efficient, widely available, just to use, just to start off. This is, I would recommend for our novice researchers at early stages. I think it's at this point in time, it works very well for analysis purposes.